So I believe it's ready. So actually, the setting for the hybrid lecture is it's a little bit complex. So it takes time. Also, so as I announced, sorry. As I announced in the Blackboard, so we will use the Blackboard attendance check system. So actually, before starting this hybrid lecture, it's actually the in-person lecture. So I used the Zoom registration for checking the attendance of students. But we cannot use this because so some students attend the in-person lecture, and then some students also attend the Zoom meeting class. So, so we will use the Blackboard attendance check system. And then unfortunately, you need to check the attendance on Blackboard before 2:05, I believe. So I tried to adjust this time duration, but I failed to find the way. So sorry about that. Also, I posted the latest submission penalty rule for the assignment and lab assignment. It's a homework assignment and then a lab assignment. So please note that there are latest submission rules in this course. Okay, before starting today's class, so I will review the quiz. Actually. So these are the quiz problems. So what are answers? What is the answer for the problem number 1? It's very easy. so if you take the this computer architecture course, then try to remember the Moore's law. So actually, this Moore's law is very important law in the semiconductor industry, also in computer processor industry. So what is Moore's law? It's number of transistors. So Moore's law just mentioned the number of transistors, so which is related to the size of a single transistor. And then the number of transistors will be double every 2 years. This is Moore's law. And then question number 2, mark true or false. A is true or false. It's false, right? So right, what is the latency? So actually, in the first question, I asked about the latency of the single thread. Actually, I need to mention the single thread, but to me, actually, the intention of this problem is to ask about the latency and throughput. So with the multi-core architecture, we cannot improve the latency of a single thread. That means the latency is performance of single thread application. But what is the advantage of a multi-core architecture? We can increase the throughput, okay? Because with the multi-core architecture, we can run multiple threads. So that means the multiple applications concurrently. So, and then question number 2B, we can improve the throughput using higher clock frequency. Is it true or false? It's true, right? It's true. So if we increase the clock frequency of the computer processor, then we can increase the performance actually easily. And then, which means if we increase the performance of the computer processor, then we can complete the same job within a shorter time. So which means we can also do another job if we complete some previous job earlier, okay? So which means we can increase the amount of workload with the high clock frequency. So number 2B is true. Is there any howling here? And then number 3, which one is faster? So we can calculate the execution time, like instruction count multiplied by CPI multiplied by T. And T is the 1/f. Can I hear some howling here? So in this problem, IC is the same. So CPI is different. So for the CPU A, it's proportional to the 1.0 divided by 1. So it's about the 1. And then the CPU B is 2.5 divided by 3. Is something like 1.8, blah, blah, blah. But this is execution time. So which one is faster? This one is faster because it's execution time. Okay, so very simple. Okay, let's move on to today's class. 좀 들리지 않나요? So, okay. Okay. So you mean the 8 great ideas in computer architecture research, right? Okay, so but after the regular class time, okay? Okay, because this is the out of topic of the today's class. Okay. Here is the okay. Okay. In the previous class, we learned about some several instruction types in the RISC-V ISA. Also, we learned about the operands in the RISC-V ISA. 들리는 것 같지 않나요? Is there an echo here? No? Okay, sorry about that. So firstly, we learned about the arithmetic instructions in RISC-V ISA. So what are the arithmetic instructions? It's the instructions for add arithmetic operations such as add, subtract, multiply, and divide. So and then we learned that these instructions have the same format. So it looks like add A, B, C. And then sub instruction, other arithmetic instructions have also the same format like sub A, B, C. Because these instructions share the same format, so this is called the regularity. And then if the regularity is achieved in some ISA design, then we can make the simpler hardware. And then simpler hardware means that we can increase the clock frequency in the hardware, which means we can also increase the performance. It's good. Also, actually, we will learn about how to implement these assembly instructions into the machine instructions, like the machine code. But in order to explain about some several types in the RISC-V ISA, I showed these several core instruction formats in RISC-V ISA. And then I explained that arithmetic instructions. These instructions use this R format of the RISC-V ISA. So these instructions are also called R-type instructions, because this format is called the R-type format. So if you see these instructions, the arithmetic instructions require 3 operands, like 3 register data. right? So R-type instructions includes also 3 register numbers, because we can access the data stored in the register file with the register numbers. So we need to specify register numbers in the instruction. Okay, also, and then we learned about the operands, and then we learned about the 2 types of operands in the previous class. So register type operand and memory type operand. So if you take this course first, for the first time, then you may not be familiar with some concept of the register, because it's some hardware concept. So actually, in a high-level language code, we cannot access the register data directly. So in a high-level language code, we just declare the variables, and then with the variables, then we can access the data stored in the variable. So actually, the processor, the instructions in the CPU just access the register data, except the data transfer instructions, such as load and store. But so this data type is not shown to some users, so high-level language coder. So we are not familiar with the registers, but just remember that the registers are the very small memory. So it's called the register file because it's the group of registers. So just remember that registers are the very small memory. And then many instructions, many RISC-V instructions just use the data in registers. Okay. Also, in the previous class, I mentioned that the result of the instruction. The result of the instruction is the change of state. And then I said that the state means the data in memory components, like data in register files and data in main memory. So usually instructions use the data in these register files. And then some specific instructions, it's a RISC type instruction actually. So data transfer instructions can access the data in main memory, okay? So just to remember. And then this figure shows some structure of the register file in the RISC-V processor. So as you can see, the register file in the RISC-V includes the 32 general purpose registers. So which means that we can store any data, any type of some data in these registers, But you need to remember that X0 is some special purpose register because X0 always has the value of zeros. So which means some data is stored with this instruction, this exemplar instruction. So some data can be stored, but this value of X0 is not updated. Okay. And so the RISC-V has some special purpose registers called program counter. But I will not explain about this program counter later. So just remember that this is some special purpose register. Okay, so actually this high-level language code can be translated into these assembly instructions using registers like here. And then memory. So some instructions can use data in memory. Okay, so actually the arithmetic instructions only can use the data in register files, but the registers are very small. It's very fast. So it's good for the performance, but the disadvantage of the register file is that it's very small. So large amount of data cannot be stored in the register file. So actually, every data used by computer programs are stored in the main memory. So in order to use the normal instructions, like arithmetic instructions, the data in main memory should be transferred to the register file. And then, the arithmetic instructions can only update the data in register file, which means, so if we just perform the A equal B plus C, and then if this instruction can be performed using add instruction, right? But the final result, the A is still in the registers, not main memory. So this result should be transferred to the main memory also. This is the store instruction. So I also explain about the address and then data in the memory space like this. Okay, also we learned about the little endian and the big endians of the memory allocation. Okay, so this is the example code to use the array data type, and then how this high-level code is translated into the RISC-V assembler. So actually, if this high-level language code is shown in the problem or in the homework, then you need to focus on some settings or configurations. So settings in this code, so that means that the configurations in this code is that H. So it's the assumption. The data of this variable H is already in X21. Okay. So the data of H is stored in the register file. And then base address. I also explained about the base address of the array data type in the previous class. The base address is the address of, so I use the AND operator, address of A0. Okay. Then what is the address of A1? It depends on the size of a single element in array A, right? So actually, we need to know the data type of this array type, okay? But usually we are learning about the 64-bit computer system, and then also this is the load, actually load double word instruction. So we assume that the size of a single element in the array A is 64-bit, which means it's 8 byte. And then we learned that the most of the computer system use the byte address. So that means that the address 1 means 1 byte. So the size of the single element is the 8 byte. So that means the address of A1 is equal address of A0 base address plus 8. Right, okay. Then we can easily calculate the address of this A8, okay? So in order to support the offset operation in the array type data, the RISC-V also supports this type of load instruction. Actually, the load instruction is composed of, it's the destination register file, so RD, and then this is the offset, and this is the base address of an array data type. So this is actually source register. We can access this data from the register file also. So if you see this assumption in this high-level code, you can find the base address of A is in X22. So these some settings or configurations are also explained in the problem. Then how can we access the A8? So we assume that the A8 is in the main memory because there is no explanation about the A8. So we can use the load instruction. With the load instruction, the data in main memory, so we can, it's not working. Okay. So X122 has the data of base address here. And then we know that in order to access, calculate the address of A8, then this is the A0 plus 64. So with the offset and then base address, we can calculate the address of A8. And then with this address, then we can access the data stored in the A8. And then if this data is read from the main memory, and then by this load instruction, the read data is stored to the destination register X9. And then we need to perform the H plus A8, right? And then by this load instruction, data of A8 is stored in the X9. And then H is X21, so it's like H plus X9. H is the X21. And then it is also, it can be also stored in the X9, okay? So this is the actually temporary data, which means actually the A12 is allocated in the main memory, but the result of the H plus A8 is stored in the register file. So because A12 is in the main memory, and then if this data should be updated. So how can you update this data? So actually the result is in the X9. So we can transfer the data in the X9 to the space for A12, okay? So this is the store instruction. You can use the store instruction. So in the store instruction, actually the format of the store instruction is similar to the load instruction, but you need to remember that in the store instruction, this register is the also source register. So in the load instruction, this register is the destination register, okay? But store instruction reads data from the register file. Also, in order to calculate the address, target address, the store instruction need to read base address data from the register file, okay? So this address is calculated, and then with this address, the data is stored in the main memory, okay? So actually, there are different kinds of load and store instructions in RISC-V ISA. So actually, we can distinguish these different load and store instructions based on the size of data. So actually, in the previous example, we use LD. So actually, this LD means load double word, okay? So we can find the different load instruction like here, LB, LH, LW, and then also LD. So if we use the IV128I instructions, then we can use the LQ. So code word. So LB means the transferred data size is just byte. So which means, so 1 byte data is read from the main memory, and then this 1 byte data is stored in the register file. But we learned that in the IV64I, the size of a single register file is 64-bit, which means 8 byte. So, but this load LB, instruction just transfer the 1 byte data. Then how can you fill the remaining 7 byte in the register file? So we can, so in this case, the RISC-V assume that the data is the signed data. So, okay. So what is the signed data? So data has signed bit, so we can represent the negative number with this signed data. But we can also handle the unsigned data. So if the signed data is transferred by, this is a load byte, then we need to extend the signed bit. So which means remaining 7 byte of register file data is filled with the signed bit of this 1 byte data. So the sign extension is required. But if we just handle the unsigned data, so we can use the LBU, this means the unsigned data, then we can, in this case, we just fill the zeros for this 7 byte data area. Okay. Also, there is another load instruction called LH. So data size is half word, which means 2 byte, and then load word. So the data size is the 4 byte, so 32 bit, and then we can use the LD. So if we use LD, then we can know that, oh, the data size is the 8 byte, okay? And then store is the same. So SB means the byte, SH is a half word, SW is the word, and then SD. So the transferred data size is double word. Okay, and then, so we can compare the register and the this memory. Then I mentioned that in the most of the instructions in the RISC type ISA, actually the RISC-V is the RISC type ISA. So most of the instructions in RISC type ISA just handles the data stored in the register file. So it is because the register file is small, but it's very fast. So which means if the instruction just accesses the register file, then we can complete this instruction quickly with the fixed clock numbers. But memory is very slow actually. So in order to access the main memory, so it may take hundreds or even thousands clock cycles. So we will learn about the memory hierarchy in the chapter 5, because so just to remember that the main memory size is very large and it's very, very slow. So in the RISC type ISA, the data transfers are only handled by data transfer instructions, or these instructions are called memory instructions. And then the RISC-V, there are only 2 types of data transfer instructions, and load and store instructions. Okay, so register file is very small, but it's fast. Main memory is large and slow. But we don't need to worry about how to use this register file, because actually we just write the code with the high-level language code, and then actually when this code is compiled by compiler, then assembler code or machine code is generated. And when the code is compiled, the compiler assigns the appropriate registers. Okay, so it's also software, but with this software, the registers are assigned, and then we don't need to consider about how to use registers in the high-level language code. Okay. And then I will explain about another operand type. This operand type is called immediate type. So, immediate. And then sometimes we use this abbreviated form, IMM. So what is the immediate operand? So immediate operand is not just a constant value. Okay, but the size of this constant value is small. Okay, so let's see this example. This is the add I instruction. So I means this is the immediate instruction. Okay, what is different? So this is the destination register, and then this is the RS1, one of source register, and then RS2 is changed to the constant number. So RS2, but it's not RS2. This is the immediate value. So instead of using data stored in the registers, these constant values can be included in the instruction. So why? So why this small constant value can be included in the instruction? Because it has a benefit, so advantage. So what is the advantage of using immediate value? Okay. Yeah, right. That's right. So think like this. So we want performs the A+1. So in order to perform this A+1, if we just use the register operands and the memory operands, then how can we calculate this statement? So we can calculate like this: A is A, but B equal 1. So we need to store the data to some memory space, and then we need to perform the A plus B. So which means in order to use the data, then the data stored in main memory is transferred to the register file. But if you write the program, we frequently use the very small constant number, like 0, 1, 2, blah, 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 -1, -2. So we frequently use these small size constant number, like I plus equal 2, like this. And then, which means if we frequently use this small sized constant number, so actually in order to use the RS2, then we need to specify the register file number, okay? But there are 32 registers in the RISC-V ISR, so which means in order to represent this register file number, we need 5 bit. So because 2 to 5 equals 32. No, not 2, right? Actually, right. So we need the 5 bit, right? But with this small number, if we can just include this constant number in the instruction instead of a register file number, then we can directly use this constant number. Okay, and then this constant number is included in the register file, then we don't need to access register file, or we don't need to access memory. So we can improve the performance of our computer system. So which idea is applied in this case? So small constants are common. So which means small constant numbers are frequently used. And then we make this common case faster with the immediate operands. Okay, by doing this, then we can also improve the performance of the overall system. Okay, and then I briefly mentioned the I briefly explain about the signed and unsigned number. And I believe if you took the digital logic design course, and then I believe you already know about the signed and unsigned number. So I briefly explain. So actually, I already explained. So actually, the computer processor handles the binary number, the binary data, which means each digit of the this number is composed of 1 and 0 only. And then each digit, the size of the each digit represents the 2 if the ith digit, then which means the size of this ith digit is the 2 I minus 1. So and then it's also same to the decimal number actually. So right, because it's a binary number, but we are using the decimal number, and then each digit of the decimal number represents the 10 to some digit number. So if the unsigned number is used as the data in the computer system, then every bit, so every number represents the positive number. So we can calculate the size, the number like this, and then this unsigned number has only have the positive number and 0. So range of this unsigned number is 0 to n minus 1. So n is the bit size. But we can use the signed integer, signed number. And then for the signed number, we use the 2's complement number system. What is the 2's complement number? The MSB bit, the most significant bit in the number is represent the minus sign. Also, is the size of this MSB is equivalent to the minus 2 to n minus 1. Okay, this is the signed number. So which means if we just see the MSB, which means the most significant bit of this signed number, then we can easily know the sign of this number. Then what is the range of this signed number? Minus 2 to n minus 1, because the most negative number is the 1, 0, 0, 0, 0, 0. And then the size of this 1 is the minus 2 to n minus 1. So this is the most negative number. And then what is the most positive number? Is the 0, 1, 1, 1, 1, 1. So the size of this most positive number is the 2 to n minus 1 minus 1. Okay, easy. So, but important thing is that the MSB bit 36 is the sign bit. So if there is so actually in the RISC-V processor, so like some add instruction. So these instructions handle the data in the register file like the signed number. Okay, so we assume that every data is the signed data. But as I mentioned, load instruction like LB, if this kind of instruction is executed, then we need to define we need to know the target number is the signed number or unsigned number. So why? If the LB is executed, then we need to fill the remaining part. So like 7 byte remaining part as with the signed bit or zeros. So if you handle the unsigned data with the LB, then we need to apply the zero extension. And then if we just handle the signed number, then we need to apply the sign extension. And then required operation is different also. Zero extension means that only zeros are filled, but sign extension means that the remaining parts are filled with the sign bit, which means MSB. Okay. And then how can we calculate the minus operation, like the inverse of the sign bit? And it's actually easy. So we can apply the NOT operation to bitwise NOT operation to the data, number data, and then we just add 1 for this inverted data. So this is the required operation. Okay. And then as I explained, so sometimes we need to use the sign extension node or zero extension node. So and then so default condition of the that means that the default assumption in the RISC-V instruction is that RISC-V instruction think that the default data type is the signed data. So which means, so if we just use the LB, so and then if there is no U after this LB, then which means that the LB is handling signed data. And if we just handle the unsigned data, then sometimes this U is included after the name of instruction. Okay. Okay. Any question? Slide number. Oh yeah. So actually, this example shows the sign extension, right? Because when the +2 is represented with the 8-bit, then this is the MSB bit, MSB. So you can find that the sign bit is the 0. And then if this 8-bit data is extended to the 16-bit data, then we need just to repeat this sign bit, the 0. So if the number is the positive, and sign extension and the 0 extension is the same, because just repeat the 0, right? But if the number is the negative number, then the sign bit is 1. So these same ones are repeated. So this is, so actually these are all sign extension, but for the positive number, the sign extension is actually the same to the 0 extension. Okay. Mm-hmm. 그렇죠. 네, 그렇게 해야 되죠. So yeah. So he asked about that. If we apply the 0 extension, and if the MSB is 1, then what will happen? So that is the 0 extension. If we just use the unsigned data, the MSB, if the MSB is 1, which means it's a very large number, right? Because it's the positive number. And then if we extend this data to the large sized data, then we can just add zeros. Okay. So for the unsigned number, only 0 extension should be applied. Okay. Okay. So, and then let's learn how to represent the assembly instruction to machine instructions. So the title of this topic is the representing instructions in the computer. Okay. So think like this. So this is example, add x1, x2, x3. So this is the RISC-V assembler instruction. But computer processors cannot understand this instruction because computers can only understand the digital data, so which means the data should be represented with 0 and 1 only. Then this instruction should be also translated into the digital data. So we need to also consider how to represent this assembly instruction into this machine instruction. Okay. So instructions should be encoded in binary. So that's why the execution files are called binary files. Okay. So, and then, as I mentioned, the assembly instructions should be translated into the machine instruction. Okay. So think like this. So this is the assembly instruction. Then we need to represent this with the 0, 0, 0 or 1, 1, 1, the digital data. So how can we represent? How can we define? So first, we need to define the size of the instruction data. Okay. What's the size of instruction data? So in order to represent this instruction, we can use the 6-bit or 16-bit, 32-bit or 64-bit. So we need to decide the size of data. Okay. How can we represent this instruction? This instruction. So actually, in the RISC-V ISA, the size of a normal instructions is 32-bit. So which means this add instruction is translated into the machine code, and then the size of this single machine instruction is 32-bit. And then I said normal instruction. And then in the RISC-V, this instruction size is the same for different instructions. And then if you read the RISC-V ISA, RISC-V ISA also support some different type of instructions. It's a small sized instruction. It's a 16-bit instruction, but it's some special instruction. So these instructions will not be covered by this course, okay? Also, if you are interested in the ARM ISA, then I believe some of you heard about the DOM instruction. So ARM also supports the small sized instruction called DOM. So ARM is ARM, and then DOM is here. So the small sized instruction in ARM is called the DOM. So this is very, actually the RISC-V also supports the small sized instruction, but I will not explain about this small sized instruction. And then usually in the ARM ISA, the size of ARM instruction is also 32-bit. It's the same to the RISC-V size of the RISC-V ISA. And then, which means, so we decide the size of a single instruction. So which means we will use the 32-bit data to represent this instruction. Then how can you represent this instruction? So in order to represent this instruction, which information is required? We need to distinguish add. So we need to represent add. And then this add instruction has 3 register operands. So which means we need to represent RD, destination register with the register number, this one. And then we need to represent X2 and X3. These are two source registers, as RS1, RS2. We can represent these registers with the register numbers. So which information is required? We need to represent add, so which means that we need to distinguish, specify, add, and then we need to define destination register numbers, source register numbers 1, and then source register numbers 2. Okay, so these information should be included in the machine instruction, right? So please remember this. Also, we need to consider regularity. Regularity is also important to make the instruction format. And then if the regularity is achieved, then we can also design the simpler hardware, so it's better hardware. So, and then I mentioned that the size of a single instruction is 32-bit, but it's not easy to represent the 32-bit with the binary number. Okay, right? So we frequently use the hexadecimal number. So with the hexadecimal number, we can represent the 4 bits with the 1 digit of a hexadecimal number. Okay, so instead of using 32 bits of a binary number, we frequently use this hexadecimal number. Okay, and then let's see the type of the instruction. It's the format of the instruction. So I mentioned that the size of a single RISC-V instruction is 32-bit. So which means this 32-bit data includes the 32 1 or zeros, so binary data. And then we can represent some bits in bits with the bit number. So we frequently use this notation like 3, 1 down to 0. So which means that this notation means this data has from bin number 31 to bin number 0, which means this data has 32 bits. Okay. And I also mentioned that in this 32-bit data, we need to include the just instruction information. So like some instruction type, like add or sub. Also, we need to include the operands information in this machine instruction, 32-bit machine instruction. And then based on this instruction, then we can also define the required format for each instruction. And then in order to achieve the regularity, RISC-V also defined the several typical instruction format. It's like called the R-type instruction, or I-type instruction, S-type instruction, or U-type instruction. So, and then as I said, so most of the arithmetic instructions used has the R-type format. So what's the like add, x1, x2, x3. So this is the example of arithmetic instruction. And then these arithmetic instructions have destination register number and then 2 source register numbers. Okay. So if you see that this R-type format, so we can find that this format includes the oh, destination register number. And then I said RISC-V has 32 general purpose registers. So we require 5 bits for representing each register number, right? So we need the 5 bit for RD. And then also RS1, RS2 are required. So RS1 is here, another 5 bit. And then RS2 is here, another 5 bit. So we consume 15 bits, and then we can use the remaining 17, right? 17 bits for specifying instructions, like this one, add. So in order to specify instructions, we can use the OP code field here, and then function 3, and then function 7 field. Okay, so using this field, we can specify this instruction. And then, so I also explain about another type, I type. So I type means the immediate instructions. So immediate. And then for this I type instruction, so we can use the add I. So this is the immediate add x1, x2 is immediate value. So if we see this immediate instruction, then immediate instruction includes the RD and then RS1 and then immediate field. So you can find the RD here, 5 bit, and then RS1 is here. And then for the immediate number, we RISC-V assigns the 12-bit immediate field here. Okay, so RS2 is not used, and then using this function 7 field and then RS2 field, the immediate number occupies these fields. Okay. Also, load instruction. Load instruction has the x1. This is the RD, and then offset. Actually, this offset is the immediate value, and then RS1. This is base address. So load instruction has also I type. So I type format. Okay, and then S type is the store instruction. So store instruction requires the 2 source registers. And so you use the RS1 and RS2, and then immediate numbers are allocated to the RD and then also function 7 field. And then U type is the jump instruction. So we will learn about the jump instruction later. So it's a regular, so we can, RISC-V defines the regular formats for different instructions. And then with this regular format, we can represent the different instructions and required operands. Okay? Actually, I explained. So this is the R format instruction, so R type instruction. As I explained, the RD is here, RS1 is here, RS2 is here. Like add RS1, add RD, RS1, and RS2, like this. And then using these function 7 and then function 3 and the OP code field, the add is specified. So this is the example. So this is the add x9, x20, x21. This is the RD, RS1, the RS2. So in this example, the RD is 9 because the destination register number is 9. So we can view 9 here. And then with the binary number is the 01001. And then RS1 is here. So we can view 20 here. So it's 10100. 21 is here. So it's a RS2. So here RS10101. And then we need to specify add. So I said using the OP code and then function 3 and then function 7 field, then we can specify add. So this is the OP code field for add. This is the function 3 field for add, and then function 7 field for add 0051. So we can represent this number as the binary number. And then if we concatenate these all binary numbers, then we can build the instruction, the machine code, machine instruction for this add x9, x20, x21 here. So computer processor reads this instruction. It's a binary number, binary data. Okay, and then this is the instruction. This instruction is given to the processor. So, and then based on the definition in instruction set architecture, computer processor decode this instruction. How? The computer processor hardware already knows that, oh, this field is the OP code field, or this field is the RD, function 3, blah, 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 blah. So just split this binary code, binary instruction. Where is the cursor? Just to split this binary instruction, like here. Oh, from pin number 0 to 6. Oh, this field represents the OP code. And then, oh, split these 5 bits. So, oh, this is the RD. And then this is the function 3. This is the RS1, RS2, and then function 7. So, because these rules are defined in ISA, the computer processor hardware is designed based on these decoding rules or encoding rules. So this data, this binary data is given to a processor, then processor decode this binary data, and then based on this the instruction encoding rule, the processor decodes this binary data based on some predefined field. Okay. So, and then I will show another. So, then how can you specify the different instructions? Where is the Zoom? I cannot find the Zoom. Oh, here. Sorry. Okay. Actually, in this Excel file, I summarized some RISC-V basic instructions. So actually, this Excel file is very similar to the RISC-V green card or RISC-V reference data, but I just added this field, like the format field. This format represents some R type or I type instructions in RISC-V. Also, I showed the OP code and then function 3 or function 7 field for each instruction. So if we want to use the add instruction here, so just to see that this row, we can find the add instruction is R type instruction. So which means add instruction requires the storage register file operands, and then we need to fill the other fields like OP code and then function 3 and then function 7 field for this add instruction. So with OP code field, we can select this one and then function 3 field here and then function 7 field is here. So if we just fill this field with this predefined number for add, then we can make the add instruction, the machine instruction for add instruction. Then how about the immediate instruction here? So in order to use the immediate instruction, then OP code field is different. So for example, so this is the add. Oh, it's very small, sorry. So in order to use the add I, then we can find that this OP code field is different from R type add instruction, right? But the function 3 field is same. And then because the function 7 field is also used for immediate data, we cannot use the immediate function 7 field for the immediate add instruction. Okay. So this is the rule. Also, we can easily, so if we just see the this table, then we can easily find that OP code just decides some specific type of instructions. So for example, if OP code field is like this, is a yellow colored, then this is the load instruction, right? And then the type of load instruction is the I type. And then as I explained, load instruction also includes the immediate data. How about the store instruction? The type of store instruction is different. So store instruction is the S type. And then we can find that OP code for this store instruction is the 01, 00011. And then for the R type instruction, like this shift arithmetic logical instructions, for the R type instructions, the OP code field is the same. So for the shift arithmetic or logical instructions, if we use the R type instructions, then we need to use the OP code like 011, 0011. And then if we use the I type instruction, then OP code is here. And then also there are different type of instructions such as the compare and then branch instructions. The OP code is also different. Okay. So if you see this Excel file, I also posted this Excel file on the Piazza, then we can easily find how can we encode the OP code field and then function 3 field and then function 7 field for the specific instruction. Okay, and then also we can find the type of instruction here. So actually the RISC-V is very simple. So I believe you can easily understand how to represent the assembly instruction into the machine code instruction. Where is the Okay, so for the immediate type, so as I explained, the immediate type is a little bit different. So, but actually this RS2 and then function 7 field of the R type instruction is R type field are used for immediate data. Okay, so actually the same. If you can understand how to represent the R type instruction with the machine code, then I believe you can easily understand how to represent the immediate type instructions. And then S type is also very similar, but one difference is that S type instruction does not have RD. S type instructions have two RS RS number, the source register numbers. And then I will explain about the stored program computer. So if we just see this instruction data, so binary data, then this data is actually the same to the normal data. So if we just see this binary instruction, then if we cannot distinguish this data with the normal binary number, right? So actually, instructions are data. So, which means instructions are also stored in the main memory. So think like this: if you, in order to execute some binary file, then we just click this binary file. So if you use the Windows operating system, where we just execute the binary file. So this is the file. What is the file? File is simply the group of data, group of binary data. So if we just execute this binary file, then the binary file first move to the main memory, which means the instructions. The binary file includes the instructions. The instructions are also stored in the main memory. And then these instructions are transferred to the computer processor, and then computer processor execute these instructions. This is called the stored program computer model, which means instructions are also stored in the main memory, just like other data. And then the instructions are accessed by address, because in order to access the data in the main memory, we need to know about, we need to use the address, right? So with this address, the instructions are accessed, and then instructions are transferred to the processor, and then processor execute instructions. So this is the stored program computer model, and then actually most of computers use this model. Okay, so but you need to think like this. In order to access the instruction is in the main memory, so which means we need to know the address of instructions, right? This address of instruction is called program counter. So with this program counter, the computer processor accesses the instructions. So I skipped this special purpose register here. So you can find, oh, this is the PC. PC means the program counter. So program counter value is also stored in this PC register. Okay. So I also explain about the detail in the later. Okay, I will stop here, and then any questions? Okay, thank you for your attention, and then see you in the next class. Thank you, guys.